Okay, guys, so I'm going a little weirdly out of order from your book today. I'm kind of hitting several sections at once. I'm going to get all of these bits kind of scooped up together. I'm just not really presenting them in quite the order that your textbook is, but the same information is going to be here. So we talked about ions, what they are, how they're formed, how to predict what ions are going to form for a particular compound, for in compounds. So remember, just by way of review, that like if you see chloride, you can predict that in a compound specifically, remember I can make all sorts of weird charges on chlorine in a lab, but when it forms ionic compounds, it's going to be a -1, and you should be able to predict that from the periodic table because it's in group 7, it has 7 valence electrons and it wants 1 more to complete its octet. So here's the deal. Atoms can gain or lose electrons, but they can't just, chlorine can't just decide that it wants an extra electron and then get an extra electron and be negative, right? It has to come from somewhere else, right? And sodium can't just decide that it wants to just get rid of the electron. It's got to find somewhere to put it, right? So these two kind of ideas work together. What actually happens, and this is why, so this is the basis for ionic compounds. The idea is electrons, one atom has to gain electrons and the other has to lose it. So if we think of sodium, and we think of chlorine, just the elements themselves, if we look at the Lewis structures, the Lewis symbols, right? Sodium has 1 valence electron, chlorine has 1, 2, 3, 4, 5, 6, 7. So what's going to happen is sodium is going to lose its electron to chlorine, right? So when we do Lewis symbols for ionic compounds, right, we have to show something else is happening here, because what happens is there's now a charge. So I'm showing the correct number of valence electrons, but in a Lewis symbol, when something is an ion, which these now are, remember sodium now has a positive charge because it lost an electron. Chlorine now has a negative charge because it gained an electron. We show anything, when we're doing Lewis structures, we show anything that has a charge in brackets, and we put the charge outside of the bracket. Now, that has happened, so sodium is going to lose its electron to chlorine, and now they both have their octet. They both have their noble gas electron configuration. One thing that's important to remember is sodium and chlorine, sodium is very reactive, usually because it wants to get rid of this electron. Chlorine is really reactive because it wants to gain an electron. Remember that the valence electrons dictate the chemical behavior. So now that they both have achieved an octet, right, they're both going to be basically inert like noble gases. They're not going to be reactive anymore. This is why ions act very differently from their parent atoms. The only thing that's really relevant now is the fact that they had to come in very close contact to trade electrons, and the sodium has a positive, the chlorine has a negative charge, so what's going to happen is they're going to stick together, positive and negative, right? This is the basis for an ionic bond. So, it's important to know that when you take sodium, and I'm not going to draw them in Lewis form, I'm just going to draw them like this, sodium and chloride, when they come together, the overall ionic compound is going to be neutral, right? It's not going to be a compound unless it's neutral. So 1 sodium and 1 chloride ion are going to come together and make it neutral. Now, it has to be neutral for a couple reasons. One, it's not considered a compound if it's not neutral. But secondly, in order for sodium and chloride started out neutral. So in this mess, right, there is an equal number of protons and electrons. We're just shifting 1 electron from one to the other, but overall, the number of electrons has to be constant. So we're not going to have something that has a charge. So the total charge from the cations has to be equal magnitude to the total charge of the anions. So as I said, sodium and chlorine, right? Sodium wants to lose its one electron to chlorine, right? And so we get sodium plus 1, chloride minus 1, we get sodium chloride. Now imagine sodium and oxygen. How many valence electrons should oxygen have? 6. Hopefully you said 6. So, sodium is going to lose its electron, right, to oxygen. So we get sodium plus and oxygen -1, right? But this isn't really enough, though, right? Because oxygen doesn't have an octet, right? Oxygen doesn't have enough electrons. Now, it's basically impossible for me to take two atoms, take tweezers, and push two atoms together. So if you ever are reacting to substances, you have a nearly endless supply of either element, right? So the idea is that while you have sodium and oxygen are very happy up here, what's going to happen is another sodium is going to come nearby, and oxygen is going to say, oh, I need that too. And so what happens is the whole thing ends up looking like this. Na plus O and Na. And it doesn't really matter where I put the two, right? It doesn't really matter where I put the two sodiums. What's important is that in order for everyone to be happy, we need two sodiums to match the one oxygen. And I did the charge on oxygen wrong. It should be 2 minus. So, and overall, another way we can think about it, so we don't have to draw out the Lewis structure every time and push the electrons around, even though that is where this is coming from, it has to do with toweling up the electrons, is I can just think about it in terms of charges, right? Sodium is going to naturally want to form a plus 1. And it looks like a 4 now. Sodium plus. Oxygen is going to tend to want to form minus 2. What's going to happen is we need two sodiums, right? So we have a total of plus 1, plus 2, minus 2. It has to be neutral. Now the way I'm going to write that formula is Na2O. So, since the total loss of electrons has to equal the total gain, the overall ionic compound has to be neutral. So, we can figure out what sort of ionic compound is going to form by figuring out how we can get neutrality for the compound. So here's something a little more involved. Aluminum reacting with bromide, or bromine, right? So the way to think about this is, what charge will aluminum form, right? Aluminum is going to want to form a plus 3. Bromine is going to want to form minus 1. Well, how can I combine these two together so that they cancel each other out, right? I've got I accidentally paused. I have a plus 3 over here, I've got a minus 1 over here, and so I'm going to combine them. I need 3 bromines for every 1 aluminum, right? Because 3 bromines will give me minus 3. Combine that with the plus 3, and it will be 0. It will be a neutral. All right. So, sodium and sulfide, or sodium and sulfur. It's going to be Na2S, right? Because sodium is going to be plus 1, sulfur will be minus 2. So I need 2 sodiums to neutralize that 1 negative 2 sulfur, right? It's not a matter of this number is going down here, right? Aluminum and oxygen. This one's trickier. So think about this one for a minute. Aluminum is, as I said before, plus 3. Oxygen will tend to form minus 2, right? So how can I make these neutral? Well, let's think about it this way. If I put just aluminum and oxygen together, okay, that's an overall plus 1, right? Because I've got plus 3 from here and minus 2, and that's going to be plus 1 overall. Okay, well, let's add a more negative. Let's add another oxygen. Well, now I've got a total of minus 4, and now my whole thing is going to be -1, right? 3 minus 4 is -1. Okay, we need another aluminum. Well, that's no good either, because now I've got -4 and +6, and now I've got +2. That's no good either. So let's try adding another oxygen. Now, I'm not going to have you do this trial and error every time. So now I've got +6, and -2 times 3 is -6. Oh, there we go. So you just have to figure out sort of the least common multiple, right? So aluminum is +3, oxygen is -2, so the combination that makes it neutral is 2 aluminums for +6 and 3 oxygens for -6. Some of you might be getting clever and thinking, oh, I get it. Maybe I can just take this number and swap it over here and take this number and swap it over here. I think that's a dangerous game to play. In many cases, you'd be right. However, there's something important that makes this a problem. And that is the fact that what's happening here is we're not making a molecule, right? We're making a big lattice, actually. So when sodium and chloride come together, sodium binds with chlorine, but it's not a molecule, right? It's not a molecule. What happens is another chlorine can clump around it, and this can happen, and this can happen, and you can get, what happens is ionic compounds actually exist as these big repeating lattices of positive and negative charge. It just turns out that in the aggregate, over millions and millions and millions of these things, the charge has to be neutral. So what we're showing in the formula is not like a molecule, not like H2O or CO2, where there's actually, like in CO2, you have a carbon atom and 2 oxygen atoms, and that is a molecule into itself. That doesn't work this way with ionic compounds. Ionic compounds form these lattices, and so what our formula is, when you see sodium chloride, it's the ratio. It's telling you that there's an equal number of sodium and chloride ions in that lattice. With sodium sulfide, it's telling you there are twice as many sodium atoms as sulfur atoms, or sodium ions as sulfide ions. And the ratio between aluminum and oxygen is 2 to 3, right? Or another way you can think about it is it's just the smallest neutral unit you can make. But don't make the mistake of thinking that this is actually like a molecule. So because of that, we have to reduce it. We reduce it down. So I'm coming back to why this is a dangerous thought process. So if you say take calcium and oxygen, right? Well, what's the charge on calcium when it forms compounds? It's 2 plus. Oxygen is 2 minus. If you were to write Ca2O2, that would be incorrect. It's calcium oxide because you have an equal number of calcium ions and oxide ions, right? So you can do the swapping thing, but you have to reduce it. You have to make sure you reduce it. You can't leave it like that, right? We'll see more examples of why this can be very dangerous. So yeah, it works, but just be really, really careful with it. I think it's easier to just think about what combination will make the thing neutral. What's the easiest combination to make them neutral? Rules to remember while writing ionic compound formulas. 1. You always write the cation, the positive ion first. So that's going to be your metal first, then the nonmetal. This is critical. Charges are not shown in the formula. You will get it wrong if you show me something like this. If you write this is incorrect. Charges are not part of the formula, so be very careful with it. Finally, the numbers in the formula give the ratios for the ions. They're not molecules in the sense that, like, water is a molecule. They're different. So remember back I said before that I said that there are some compounds that are not molecules. I'm talking about ionic compounds. They're lattices, not molecules. Okay, let's do a little practice. Okay, I want you to predict the compounds formed from the following combinations of metals and nonmetals. So we're going to write the formulas here. So pause it and do these. Okay, so magnesium and phosphorus. So magnesium has a charge of 2 plus, phosphorus is 3 minus. So in order to combine them so that they're neutral, Mg3p2, right? Because 3 magnesiums give me a total of plus 6. 2 phosphorus ions gives me a total of minus 6. So it's neutral. Strontium and oxygen. What's the charge on strontium? Hopefully you said positive. Oxygen is 2 minus. Oh, I'm sorry, I made a mistake. That was me being dumb. Strontium has a charge of, it's in group 2A, it's plus 2. It's early in the morning and I wasn't thinking straight. So we end up with SRO. Sorry about that. Lithium and fluoride. Lithium is plus 1, fluoride is minus 1, so LiF. Lithium is still plus 1, nitrogen is minus 3, so you get Li3N. Okay, hopefully that makes sense. I will talk more about naming, but I mean, it's as simple as that. Writing formulas is as simple as figuring out what the charge on the ions is and putting them in a combination that makes them neutral.